Okay, folks, so this is going to be the last part of Chapter 11 here, and this is where we left off, which is a triple bond. And so one of the important compounds that you all might know is welding torches, which is acetylene gas torch. These, when they're burned properly with the proper mixture of acetylene and oxygen, can reach temperatures above 3,300 degrees Celsius and thus almost instantly melt the metal and allow you to fuse together different pieces of metal together. For example, steel usually is what this is used for. The proper IUPAC name for this is actually ethyne. So alkenes and alkynes, these are going to be families of hydrocarbons. They'll contain a double bond for the alkenes, triple bonds for the alkynes. They're going to be called unsaturated hydrocarbons, and that's because they don't have the maximum number of hydrogen atoms on these structures. They, in fact, have, for alkenes, 2 less hydrogen atoms, for alkynes, 4 less hydrogen atoms. They react with hydrogen gas to increase the number of hydrogen atoms and become alkanes, and this is actually the process called hydrogenation, as in like hydrogenated fats. That's actually the exact same process. And unsaturated fats have double bonds or triple bonds, typically double bonds. And that's where actually the terminology comes from. So alkenes contain one or more carbon-carbon double bonds. For example, right here we actually see, right here we see ethene. This is the eth, or like ethane, which would have 2 carbons. It's called ethene because it has a double bond in it. And you can see hence the naming. Now notice that this actually gives us a trigonal planar structure, that triangle on one plane, which has bond angles of 120 degrees. So ethene, more commonly called ethylene, is the common name for that. It's actually an incredibly important plant hormone. This is why, for example, if you put a plastic baggie over bananas, they'll actually age faster. And so it helps promote the ripening of fruit like bananas, accelerates the breakdown of cellulose in plants, which can cause flowers to wilt, for example, and leaves to fall from trees. A little interesting factoid is that when they used to transport bananas in the holds of ships, the ethene would rapidly build up, and then if anybody opened the ship up with an open flame, it would blow the ship up. This is alkynes. These contain one or more carbon-carbon triple bonds. In this case, we have ethyne, which is going to be 2 carbons with a triple bond, which we can actually see right here. And that has a bond angle of 180 degrees. It's actually a straight line. And so one of the problems I want you to go ahead and think about, now this is a recording video with no people like watching it. They'll be watching it asynchronously like you're doing right now. And so my little quiz is going to come up. And I'm just going to quickly go through the quiz and explain. So identify the following compound as an alkene or alkyne. And so what you'd want to do is you'd want to look at this and go, is this have a double or triple bond in it? We look here, there's 2 lines, that's a double bond. And so that's an alkene. An alkane would only have single bonds. An alkene has 1 or more double bonds. An alkyne has 1 or more triple bonds. So here we have 3 bonds right there. And so that right there is actually a triple bond on this one. And so that one we have an alkyne. All right, so let's name some of these according to their IUPAC naming. What we're going to do is we're going to take any of the alkane names that we would have named before, and if we have an alkene, we'll just change the ending to ene, E-N-E. If we have an alkyne, if we have a triple bond, we're going to change the ending name to yne, Y-N-E. And we're going to have to indicate where along that chain this double or triple bond is. And so we'll end up giving it a locator number. So let's go ahead and write the IUPAC names for each of these following compounds. Now keep in mind the first thing you do on any IUPAC naming is you count off your carbons. 1, 2, 3, 4, 5. So that's would normally be pentane. But we have a double bond in this, so that's going to be pentene. This one right here, we have 1, 2, 3, and then another one here, which is 4, 5, 6. So this would normally be hexane if it only had single bonds. But it has a triple bond, so this is going to be called hexyne, Y-N-E at the end. And so right here we have the base name for these. We have the main chain name. We're actually done with this one right now, except for giving it a locator and saying, hey, where is our triple bond? For this one here, though, we actually would need one more thing, which is the prefix. So let's get our locators first for these double and triple bonds. These are going to be very high priority in naming these. These are going to be very important. And so we'll go ahead and give them the lowest possible number. This is 1, 2. So this is going to start with a 2. And this will be 2-pentene. This one right here, we would get a very high number if we count off from left to right. So we're going to go from right to left. 1, 2. And so that's 2-hexane. So here we have 2-pentene, excuse me, and 2-hexane. All right, so this one here is done completely. We are done with part B. Congratulations, there's no substituents. We don't have to put any prefixes. That's just done. This right here is going to be needing a prefix. If you see right here, we have a methyl group. And so that's going to be a methyl. It's on the 4th position. If we were numbering this off, 1, 2, 3, 4. And so that's going to end up being 4-methyl-2-pentene, which is right there. That's the full name. Okay. Please make sure you practice. It is in language. I'm going to point a little something out. Please don't get confused by it, which is that this is what's referred to as the old IUPAC naming. The new IUPAC naming would actually have the new IUPAC naming would have the hex, and then we'd put a dash, 2, dash, ine. That would be the new IUPAC naming. I'm not going to teach that in this course right here because it just confuses it, and you don't need that new IUPAC naming particularly much. You can learn that new IUPAC naming if you ever need it in the future. Okay, so the last thing we're going to go ahead and talk about a bit is we're going to talk about the cycloalkenes. Now again, this is going to be like a cycloalkane, but we have a double bond in it. And so we're going to end up with a cycloalkene, meaning a double bond's in that ring. And right here we actually see that double bond in the ring. Note that whenever a double bond's in a ring, we're going to end up with the first and second carbons being part of that double bond. And so you always number off the carbons based on that double bond when it's in a ring, 1, 2, and then anything else gets numbered off of that. And so that'd be 3, 4, 5. Okay, so now the next thing we need to do is we need to talk about cis-trans isomers. So in alkene, the double bond is going to be rigid. It doesn't allow you to rotate around it. You can actually practice this by putting your 2 fingers together and trying to rotate without breaking them. And you'll see that does not allow rotation. What that means is that if you have something that's on the same side of a double bond like so, see how these 2 chlorines are on the same side of this double bond across it, versus if you have them on opposite sides of the double bond, these cannot rotate and exchange between them. And so this right here, when they're on the same side, is called cis. You can kind of remember that by cis, same side. And trans is going to be on opposite sides, i.e. different sides. And so this is where the chlorines are on the opposite sides on 2 different carbons next to each other of the double bond. Now, these cis and trans isomers, they actually have different properties. And so you can actually have a active drug, you can have a unsaturated fat that will actually react very differently depending on whether it is a trans or cis fat. You actually kind of know this already because you've heard of trans unsaturated fats, actually. Excuse me. Man, I really should have gotten water. And so that's actually where that terminology came from, is the trans unsubstituted fats. This is how you can actually model these with your hands, by the way. Cis would be where your thumbs are on the same side, i.e. above your hands. And then trans would be where you have them on different sides, i.e. one is up, one is down. So in the cis isomer, the alkyl groups here, they're attached to the same side of the double bond, and the hydrogens are going to be on the opposite side, the other side, again like that. In the trans, you're going to have these alkyl groups, they're on opposite sides, and the hydrogens will be on opposite sides as well. So many insects actually emit minute quantities of chemicals. These are usually referred to as pheromones. They're going to be used to send messages to others of the same species. Pheromones may warn of many different things, or may actually be used for several different purposes. We can warn an insect of danger, we can mark a trail, we can attract the opposite sex, of course, and so they can then attract mates from great distances using those pheromones. Now, the effectiveness of these pheromones depends on the cis-trans configuration of the double bonds in the molecules. So one pheromone is known as bombycil, and that has the sex pheromone produced by the female silkworm moth. This contains one cis double bond and one trans double bond. And this is another representation of cis and trans. So the prefix of cis or trans is going to be placed in front of an alkene name when the compound has a cis or a trans isomer, when there's a difference between those two things, which is quite a few of the alkenes. So here we're actually going to name these off and name them and then give the cis or trans prefixes where needed. So the first thing we need to do is how many carbons are there? There's 1, 2, 3, 4 carbons. That's actually true for all of these here. They all have 4 carbons. Normally that would be referred to as butane if they were all single bonds. However, this has a double bond in it, so we're going to need to recognize that, and that is now butene, okay, which is the double bond being in the 4 carbon chain. Now, this double bond, this is located at the second position, and so this one would be 2-butene. Now the next part we need to do, so this one right here is actually just referred to as trans because they're on opposite sides, 2-butene. These ones have some prefixes we have to add. They actually have substituents, chloro in this case, and bromo in this case. So the next thing we're going to do is we're going to go ahead and assign these, cis or trans, and then we're going to assign them their prefixes. So we're going to go, this one here has the carbons on the same side, it has the chlorines on the same side, so that's cis. So that's going to be a cis-2-butene. This has prefixes, which are on the second and third carbons. And so that's going to be 2,3-dichloro. And then we would be cis-2-butene. This one right here is going to be on the opposite sides. So you see they're on the opposite sides of this bond here. And so that would be a trans-2-butene. Now, this one right here is actually going to have the bromos on the second and third position. And so that would be 2,3-dibromo trans-2-butene. Now your book actually has it a slightly different way, slightly different orientation. Note that I'm always going to do these in a multiple choice manner for you. And so as long as you can assemble them, you'd be fine. The book's actually a little bit off, but close enough that it's not an issue. And so your book actually calls this cis-2,3-dichlorobutene. Technically, you should put in the 2 position for this, but they did not in the book. Trans-2,3-dibromobutene. Again, you should actually put the 2 position through the butene in here, but they did not. And then this is trans 2-butene, which they actually did exactly right. Okay, so let's go ahead and talk about addition reactions. These are going to be reactions where we add stuff across the double bond. So in alkenes and alkynes, the double and triple bonds are going to be very reactive. We can add hydrogen across these double bonds, or HO, water, across these double bonds whenever we have a double or triple bond. These are easily broken, so they provide the electrons to form the new bonds. That's because these double and triple bonds actually have these fairly loose electrons that can get snatched up into bonds pretty easily. So this is referred to as hydrogenation. So this is where hydrogen atoms are going to add to the carbon atoms of a double bond or triple bond. This is always going to need some sort of catalyst. It's very difficult to do without a catalyst. And so platinum, nickel, or palladium are the most commonly used catalysts. There's actually quite a few of these. It's a process that gets done a lot in industry, especially with food. So this is your double bond, let's say on an unsaturated fat. So you go ahead and put it with hydrogen gas boiling across it in the presence of a catalyst, like a platinum catalyst. And this is then going to turn that double bond here into a single bond with two hydrogens across it. And so right here is actually the process of hydrogenation of oils. And we add a H2 across that double bond in vegetable oils. And what this does is it produces compounds that will have slightly higher melting points. And so what would normally have been a liquid at room temperature can now be a solid at room temperature. And so we can take things like butter, margarine actually. Butter is a solid at room temperature anyways. So like margarine, Crisco, vegetable oil, hydrogenate it and it makes it that solid. Or peanut butter, peanut oil, you hydrogenate peanut oil and that gives you peanut butter. So here we're going to write the product of each of the following reactions. Remember, we're always going to take this carbon-carbon double bond. It's going to turn into a single bond with an extra hydrogen on each side. And so we take this, we break the double bond, it's now a single bond, and we get an extra hydrogen on each side. And so that CH goes to CH2, this CH goes to CH2. This one had a double bond. We don't actually have to write any hydrogens out, so we just get rid of the double bond mark, and now it's a single bond. Ta-da! We've done hydrogenation. So this is referred to as hydration. This is adding water across that double bond. And so the hydrogen atom is going to form a bond on one side, and then the OH is going to form a bond on the other side. And we'll have gotten rid of that double or triple bond. This is typically catalyzed by a strong acid. For example, H2SO4 works very nicely for this, or sulfuric acid. And so we're going to break the double bond, end up with a single bond with an H on one side and no H on the other. Hydration, literally adding water across the bond. So let's go ahead and do this product right here. So we're going to get rid of that double bond. Bam, only a single bond between these. And then we're going to have an OH and an H across here. So we add an OH to this carbon here, and we add a hydrogen to this one. So benzene, you may have heard of benzene before, or maybe BTX, which is the B in BTX is benzene. This is an aromatic compound. It has 6 carbon atoms. Each one has one hydrogen bonded to it. It is actually a flat ring structure, and it has 3 alternating double bonds. So we can actually see that, 3 alternating double bonds there, and that's that flat ring structure. This is another way of representing benzene. This is probably the most common way, and you've probably seen that actually in tons of logos, because pharmaceutical companies love using benzene rings in their logos. So these are some of the different aromatic compounds that will contain a benzene ring. And whenever you have a single substituent off a benzene ring, the benzenes actually end up with special names in the IUPAC rules. And so, for example, when we have a methyl on a benzene, that actually gets called a toluene then. Instead of calling it like methylbenzene, it's actually toluene. This is the line angle structure for that same thing, toluene again. This one has an amine off of it, a nitrogen, And so that's aniline. That's the name of that compound. And then you name anything based off of that as substituents off of the aniline. This right here is then phenol. That's the alcohol off of a benzene ring. So phenol. This right here is then going to be the naming of these aromatic compounds when you're putting different prefixes and substituents on them. So here we're adding a chloro to our benzene. And because there's only one of them on there, it's just chlorobenzene because we don't have to specify because there's only one. It'll look the exact same if we put them on any different one of these carbons. Right here we have 1,2-dichlorobenzene, and this is the first position here, second position right there. This is then 1,2,3-dichlorobenzene. Again, we have two chloros, so the first position's here, and then we give this one the third position to minimize numbers. This one's 1,4-dichlorobenzene. Again, a first, and then 1, 2, 3, 4, and fourth position. So whenever we have a toluene, phenol, or aniline, then they have substituents on them. What we're going to do is the toluene, phenol, and aniline count as the first substituent. And so, for example, we put bromo on this. We'll start counting at the aniline position, 1, 2, 3, and that gives us 3-bromo aniline. Here we have a phenol, and we start counting at the phenol position right there. So that's 1. And then the next substituent is going to be 2 to give the lowest number, which is chloro. And then the next one's actually 4, all the way down here. That's 3 and that's 4. And so the total name would be 3-bromo, 2-chloro, phenol. And again, phenol is because it's a benzene ring with an alcohol on it, this OH. This right here then is going to be, the first position is toluene, so we've named that based on this structure right here, the benzene ring with the carbon. That's toluene. And then we go ahead and number this, the lowest possible numbers. So this is 2 then. And that's going to give us 4 right here. And then 6 over here. And so all together, that would be 2,6-dibromo, 4-chloro-toluene. Just that. Now, toluene is actually used as a reactant to make drugs, dyes, and explosives like trinitrotoluene. That's actually what TNT is. It's 3 nitro groups off of toluene, which is right there. The proper IUPAC name would actually be 2,4,6-trinitrotoluene. This right here is acetaminophen, more commonly known as Tylenol. This right here is aspirin. Again, this is a substituted benzene ring, which again is medicine. Aspirin, you know aspirin. And this is vanillin. This is actually vanilla, the flavor of vanilla and the scent vanilla. So let's select the correct name for each of the compounds right here. And so again, we have a benzene ring right there, and this has a chloro on it. Now we don't actually have to number that chloro because it doesn't actually matter which one is substituted here. You would get the exact same names for all of those. And so that's going to be chlorobenzene, no number, we're done. Over here, this is another benzene ring. And so you'll see that this actually has 2 methyl groups on it. Now, correctly speaking, it should actually be methyl toluene. But for whatever reason, your book actually names this differently, which is kind of weird. But according to your book, it's actually going to be 1,3-dimethylbenzene. And that's what your book actually gives. Okay, I'm going to go ahead and put up a little naming module where I have a bunch of naming presentations on how to name stuff properly. You can use that to solve the lab stuff. You can also use that to learn naming better, which could help you out in career someday. But all the compound names around you, you've secretly been living a life that you've never really realized it, but all this naming has been constantly around you, and you never understood any of the stuff around you. There's been a world under the world that you've recognized. And that's always been this organic naming and these organic compounds that you really never realized it until you have the tools to actually understand language. Okay. You all take care. Have a wonderful break.